So, today we are going to learn about the last two types of discontinuity that you might run into with a rational function. We did discuss what happened if your rational function was a proper fraction and how that gave it a horizontal asymptote at 0. We talked about how if your rational function was an improper fraction, but the boring kind, where it's just a polynomial on the top and the bottom that have the same degree, and that always caused a horizontal asymptote, but it was at a number other than 0, so you usually had to divide the leading coefficients. So today we want to talk about the type of discontinuity when you have an improper fraction with a polynomial on the top that's degree is larger than the polynomial on the bottom, so the numerator is larger than the denominator, and what kind of discontinuity that creates. And we also want to talk about what happens if you have a rational function, but it can actually be simplified. And what does that look like or cause to happen? So we want to look first at the following function. It should provide us some examples to look at. So if I have y equals x cubed plus x squared minus 14x minus 24, and it's all over x squared plus x minus 20. All right, so this is the rational function that I want to try and find its points of discontinuity. And I know that the first thing I want to do is factor first. So I'm looking at my denominator, and my denominator, two numbers that multiply to equal negative 20 and add to equal 1 should be positive 5 and negative 4. So I've got x plus 5 and x minus 4. Now up here on the top, we have a cubed polynomial. And if you remember from our polynomial unit, that if we can find the x-intercepts, those are factors. So that is kind of my go-to factoring method. So if I type in just this top polynomial, x squared minus 14x minus 24, I'm looking for these x-intercepts, and it looks like I have x-intercepts at negative 3, 0, negative 2, 0, and 4, 0. So that means that these factors must be x plus 3, x plus 2, and x minus 4. So I factored the top and the bottom. I want to do this because it's going to help me find key features of the graph, and quite honestly, you just always want to do that no matter what when you are graphing rational functions. What you're going to notice is that my top and my bottom actually have something that will simplify. We have an x minus 4 on the top and an x minus 4 on the bottom, so those divide out and become 1. Anytime you can simplify a fraction, you should always simplify a fraction. That's going to make things easier to deal with. It makes the number smaller, it makes the graph smaller. Our polynomial is going to be a lot less going on. But what happens is when you have a rational function, you remember this was the original function, and this is what we have been asked to graph, these will not cancel out if they were equal to 0. We still can never allow division by 0 to happen. It is not allowed to happen. So that means that I cannot let x equal 4, because if x was equal to 4, then this would have never happened. It wouldn't have simplified. And so that means I'm going to end up having a hole in my graph at x is equal to 4. Now, the good news for us is we don't have to worry about graphing this whole big function. We are going to graph the simplified function. So we're just going to graph the x plus 3 times x plus 2 all over x plus 5, the simplified one. That's what actually gets graphed. But when I do draw that graph, it's going to have a hole at x is equal to 4. And I mean quite literally, you draw a hole there. Like it's an open circle. Remember, a graph, when you have a line that goes up to an open circle and then continues on, it just means it goes all the way up to that number, but cannot be equal to that number. So I need to figure out where would 4 be on this graph. So I'm actually going to plug 4 into the simplified function. So 4 plus 3 is 7, and 4 plus 2 is 6, and 4 plus 5 is 9. So 7 times 6 is 42, and then 42 divided by 9. That reduces, and it's going to be 14 over 3, 14 thirds. So it's roughly 4.6. So that means if I go over to my graph and I go to 4 and 4.6-ish, a little bit more than halfway, I'm going to have a hole in my graph. So it seems weird, but holes are the first things we find. If you have anything that simplifies, you have to figure out where the hole in your graph is going to be. So wherever I end up drawing my final graph, I just want to remember there should be a hole right there. And so I just go ahead and put a little hole on my graph right there. So now I can actually just look at the graph and decide, okay, where are all my asymptotes and all that kind of stuff. So this one, we have a vertical asymptote here at x plus 5. That means x is equal to negative 5. So I'm going to have a vertical asymptote over here at negative 5. So there is my vertical asymptote. And now we can look for the horizontal asymptote. So that's where we didn't cover this yesterday. Yesterday we said that if the top polynomial was smaller than the bottom polynomial, meaning it was a proper fraction, then the horizontal asymptote's at 0. And if they had the same degree, then it would be at some other number, but still be a horizontal asymptote. Well, this is an improper fraction. In fact, if I multiply this back out, it's x squared plus 5x plus 6 over x plus 5. It's a quadratic over a linear, and that is an improper fraction. And improper fractions do not have a horizontal asymptote. They have a slant asymptote. So it's still going to have a line that the graph hugs. It's just going to be a slanted line and not a horizontal or vertical line. And so we have to have a way to find that slanted line. So this is why last unit we did actually spend some time learning long division. So the end behavior of the graph is going to be following a slanted line, and to find that slanted line, you actually have to divide this improper fraction and turn it into a mixed number. I know, we said you would never use mixed numbers after you got out of middle school, but this is the only place you will use the mixed number. We need to actually do the division and figure out what is the whole number part of that mixed number. We don't want the remainder. We just want what do you get without the remainder. So I am going to have to do some long division to figure out what that is. So I've got x squared plus 5x plus 6, and I'm going to divide it by x plus 5. X squared divided by x is x, so that'll get x and 5x. And then when I subtract, I get that cancels and this cancels, and oh, look at that. This is my remainder. All right, I have a remainder. So in this one, when I divided it, again, I'm not interested in the remainder. The remainder is so tiny that it doesn't actually change the overall graph. But this equation, whatever you get for your quotient, that's going to be your slanted asymptote. So this slanted asymptote is going to be at y equals x. So that means there is a slanted line that this graph is going to be hugging. And so we have a vertical asymptote, and we have a slanted asymptote. And then if we actually go about and graph, let's see if we plug into Desmos here, what our graph is going to look like, and see if everything we have set up here looks like it. So if we were to put this in parentheses and divide it by, and put our denominator down here, x squared plus x minus 20. There we go. And look at how this asymptote, see how the curve is coming up to this vertical asymptote. The curve is going over here towards the slanted asymptote. Now, notice the line right here. I have my hole marked there. And so I know that this curve is not actually reaching that point. I do want to show you, Desmos knows that. When you look at it, it looks like it's a solid line. But if you actually go to the number 4, 4 is undefined. It does actually have a hole there in the graph. But I wanted you guys to see that I marked it there. I put my little hole there, and that is exactly where the hole is in the graph. So Desmos even acknowledges that there is a hole there in the graph. It's just that when you look at it overall, all the numbers leading up to it are not there. But if you go to 4 and look, they remembered to put the hole there. Now, I do want to show you this is a rational function. There is another side to this graph. I just need to zoom out to see it. And so you can actually look and see that it does have another side to it. It just was off of my graph, and so you couldn't see it when I was zoomed in up there. But we do get slanted asymptotes when we have an improper fraction. And if your rational function simplifies, then you have to leave a hole in the graph when you get there.